Hi there. Welcome to another amazing day to live on this planet and to learn some physical science, in particular some chemistry. Today we're actually going to go over the periodic table a little bit. Not the periodic table of Star Wars, but an even better periodic table than this one. So yeah, let's talk about the periodic law today and the periodic table. Our objectives today to compare the organization of Mendeleev's periodic table. He was one of the first scientists to come up with this concept of organizing the elements. And then we'll look at how his table compared to Moseley's table. And we'll define groups and periods in the periodic table. And we'll look at how the periodic table organization is associated with the number of electrons that each of the elements has, which is kind of a cool connection to make. So this is the Dmitry Mendeleev periodic table. Basically, what Mendeleev did was he was a Russian scientist that came up with this idea that maybe if we could align the elements by way of their similar properties, that we could maybe figure out some patterns. And so he kind of looked for patterns. He wasn't the only person to do that, wasn't even the first person to do that. We had a guy by the name of John Newlands who was trying to do some of that same thing. He noticed that when you put some of the elements that he worked with in orders of 8, 7 alike and then an 8th one, then starting over again, that you had some similar patterns as well. But Mendeleev is a guy that's given credit for this. And he had a couple key things that made his particular periodic table special, okay? You'll notice we've got a couple little highlighted boxes over here. And this is that group 7, again, kind of having a repeating pattern every 7, right? And then he had some other stuff that didn't quite seem to fit. They were trying to figure out what didn't seem to fit. One of them that didn't seem to fit was this one here. Notice that all of these are organized by a particular number, right? And notice that they keep getting bigger and bigger and bigger, except for in a couple instances. One of them is right here. When we go from tellurium to iodine, then there was 127 that is after 128.7 or 128 question mark, sorry, not 0.7. And so there's a couple places where there was some stuff that was messed up in terms of the order. And so one of the biggest things that he did that made his periodic table better than anybody else's was he left some gaps where things didn't quite make sense. He was willing to switch, and he was willing to say, you know what, I'm going to put this one over here instead of here because it has characteristic properties that are more like these other ones up here. And so he was willing to let that one, be over there, even though it had a lower number. Okay, and so he organized the periodic table by what's called atomic mass, except for in places like this where he was like, yeah, well, it doesn't quite work to keep them in properties, and so we're going to switch them up in those cases. And so again, he listed the elements in order of increasing atomic mass, different than atomic number, okay, atomic mass, and he grouped them with unique similar properties, and he looked at a couple different things. Like I say, he switched the order of tellurium and iodine to keep them in the similar property mode, and he left empty spaces for missing elements. This is one of the biggest things he did. John Newlands, when he came up with this periodic table, he didn't leave empty spaces. He didn't allow for other elements to be discovered and predicted. And because of that, the Royal Society of Britain basically said, yeah, we're not going with you. And, he did some good stuff, but he didn't do as much as Mendeleev did. So Mendeleev, like I say, he predicted certain things. Like, for instance, he predicted that there would be a chemical element named ecosilicon, which would someday be discovered, and it would have these properties. Now, in fact, we did eventually discover that element. It's now called germanium. And look at the similarities in the properties. Okay, even things like, well, it should bind with 4 chlorines. Okay, the densities, melting points, I mean, all sorts of stuff that he predicted were very, very close, if not spot on in some cases, right? And so this is kind of cool. And this is what made Mendeleev's periodic table become so popular, because he predicted correctly. And everybody's like, whoa, if you can predict an element that's going to be discovered next, you must know what you're talking about, right? And that's what he did. So anyway, from his work came the idea of the periodic law. The periodic law basically says that physical and chemical properties follow a repeated pattern as their atomic number increases. So what we're doing here is we're going through and we're looking at the atomic radius here in this case, and we notice that it goes down as we go across the periodic table, and then it start over on the left side again, and it goes down as we go to the right. Start on the left, goes down as we go to the right, start on the left, and it just has a repeating pattern. There are so many things about the periodic table that have repeating patterns. That's why it's periodic, right? If you think about a calendar is periodic. Wow, Monday keeps happening every single week. We get this Monday. Same thing happens with the periodic table. We have very similar properties for every single element that's along a particular column. We call them groups or families. So here is then another guy that came along, and his name was Henry Moseley. Really interesting story with this guy. But while he was in graduate school, trying to get his PhD, he came up with this idea that we should arrange everything according to atomic number instead of atomic mass. And if we can do that, then maybe all the elements will align. And in fact, they did. And so he did some X-ray spectroscopy experiments, and he said, let's order them according to the atomic number. And voila, when we did that, iodine and tellurium actually ended up in the right places. Because iodine's atomic number is 53, tellurium's atomic number is 52. So they have extra protons. Iodine ends up having, not quite as many neutrons as tellurium. And so tellurium is actually a little bit heavier because it's got more neutrons, but iodine has more protons. So if they're ordered according to the atomic number, which is the number of protons, remember that? This is the number of protons. Then you get a periodic table which works out just right, where all the properties are lined up, as well as increasing order of number of protons. All right, so that was Henry Moseley. Some more interesting stories about him that you'll get into when you hear about chemistry, including the fact that he got sniped in the head, and that's how he died. Period, yeah, right? Yeah, now you're interested, aren't you? Go look it up. So a period is the horizontal rows, okay? So going along this way, horizontal rows, those are the periods, okay? These are the periods. Oh, wait, what am I doing? These are the periods, okay? The groups or families are up and down. Now, the groups and families, that's just synonymous, right? They have similar properties, okay? That's the thing about these guys. They have similar chemical properties. And just like you might have some similarities with other people in your family, these elements have similar properties with other elements in their family. And the reason for that has to do with the same number of valence electrons. Remember, we said in the objectives we were going to tie you back into the arrangement of the electrons. Well, every element in group 1 has 1 valence electron. Okay, every element in family number 2, okay, that second column, 2 valence electrons. Go all the way over to 13. Every element in group 13, 3 valence electrons. 14, 4 valence electrons. 15, 5 valence electrons, right? So you're getting the idea here that there's a repeating pattern, and their similar properties are based upon their similar valence electrons. That's what gives them similar reactivity, okay? So we have periods, we have families, and remember that elements are becoming less metallic as you go across each period. So the ones over on the far left are the most metallic in nature, and as you go to the right, then they become less and less metallic. Once you eventually get to the, all the way to the right, then you have non-metals, right? They're not metallic. That's what we call them, non-metals. All right, so let's see if we know what we set out to today. Compare the organization of Mendeleev's periodic table to the modern periodic table. Modern periodic table, Moseley's periodic table, is organized according to atomic number. Mendeleev organized according to atomic mass, right? Define group and period. Group are the families, the up and downs have similar properties. Period, horizontal, right? And they have slightly changing properties as you go across. And organization of the periodic table to the arrangement of the electrons. Each of those columns is organized according to the same number of valence electrons. Now, I will tell you that in that middle area, in the middle spot in here, or this periodic table, it's not really a periodic table, so I can't really do that, but that middle spot in here, some of those numbers of valence electrons are slightly different in a particular row, but for the most part, they are the same. But the representative elements, which are these first 2 columns and these last 6 columns, spot on, same number of valence electrons, and that's why they have similar properties. All right, we did it. We're awesome. You're awesome. And you're learning chemistry, and your life is getting better and better every day because chemistry will make your life better. Knowing chemistry will make your life better. So have an awesome day. God bless you.